Hey everyone, and welcome back to yet another tutorial on this Auto Grad series from scratch which we are building. And I just wanted to share some recent developments with you. So if you have seen my recent video, we were somewhere here. Our forward pass was working fine. Forward pass is just fine. For the backward pass and computational graphs, we need to do some extra things, right? Right now, we are just covering the forward pass, in which we are just trying to build a computational graph which keeps track of the parent tensors and the operations that we've done, right? For example, I've given you examples of if you want to like add two tensors or multiply two tensors, or if you want to take the softmax or whatever. What steps do we need to go through? How the tensor will look like in case if I just quickly show you here. Um, so this is our current tensor definition, right? So initially we had this only shape, stride, dimensions, and data inside the tensor. But right now, since we are going to implement the AutoGrad, so AutoGrad is just is something to implement, right? It's not an easy task. So especially when you just backpropagate, and you have to keep track of the tensors, the required grids parameters, and the computation graph. It should not break at any point. So you have to keep all these things in your mind, which gets a little messy. So now for AutoGrad, we have these new features or parameters of this structure of our tensor. So grad obviously is going to be the derivative or gradient of our initial tensor, and requires grad, it's actually a check which gives an idea that whether we need to take the gradient of this or not. Operations keeps track of the operations or functions, or methods or operations that we've implemented on our tensor, and parents are the actual tensors that have performed those operations, and int number of parents are the total number of parents. So I've implemented some new functions over here. Let me just show you. All right, so we'll be so you know what, when we were working on our layer norms, so we just worked on our tensor, everything was working fine. We worked on our MHA, multi attention, it was also working fine. For layer norm class, or you can say for layer norm layer, what you do actually is you take the mean of a tensor, you row wise mean, you take row wise variance, and you calculate x hat, which is your wx plus b, and then you sorry, x hat is like x minus mean divided by standard deviation plus epsilon whole square, right? Variance whole square plus standard deviation, right? In case if I can write the formula over here, this will make much more sense. So this was our x hat. Let me show you why layer norm was actually complex, right? Let me show you why it was complex. So how do we calculate layer norm? Layer norm is something like we trying to find x hat, which is equals to x minus mean, and this, by the way, this x is actually the standard actual tensor, divided by a square root of variance plus epsilon EPS, right? It's something like this, right? So the thing is, now we have calculated this x hat. Now our actual y is going to be alpha times this x hat plus beta, right? And these alpha and beta are the trainable matrices, right? I'm not sure about this formula. It could be slightly different than this, but you can check this out later. Something like this, right? So this is actually the variance. We take the square root of the variance plus add some smallest value in case to avoid the um, zero division error. And this is our x. This s hex then gets multiplied by alpha tensor and then beta tensor. So inside our layer norm, we initialize alpha, we initialize beta, and we initialize derivative of alpha and derivative of beta as well, right? So when we take the derivative of these two, we fill these two matrices, we populate them, and then in optimizer step, we just go ahead and update these actual alphas and betas with these derivatives. So for the next iteration, we keep on doing the same thing. So now we have variance here, we have mean here, so we have scaling and shifting steps over here. That's why the layer norm was actually a little complex to cater, right? So for this, what we have done actually is we have created this new tensor called tensor mean, which works something like this. So inside our layer norm forward function, what we were doing initially was might have removed the actual function, commented out. Let me just try to show you. So layer norm forward. Uh, okay, we are inside the tensor, so this won't work. So uh, ln.c ln.c. Okay, layer norm forward. Layer norm. Okay, so in case if I show you, so we had this arena, we had this layer norm, we had this x tensor, which we're going to later calculate x hat from, and then y from, which is actually our output. So I have written these steps over here. Instead of float methods, we need tensor graph. So we need the tensor graph, which keeps track of mean, standard deviation, variance, scaling and shifting, and overall all these operations to find one output. We need to keep track of these tensor operations, and then we need to build computational graph on forward pass for every of these functions, and then we'll be updating the parameters at the end, right? So these were the methods that we need to implement: tensor mean, tensor variance, tensor add, and tensor subtract, right? So in case if I now show you what did I implement so far, so this is my tensor mean, and now it looks like something this. Initially what I was doing, actually I was just grabbing the row pointer, and I was iterating the entire row and was calculating the sum and then divided by number of columns to find the row mean. But right now I need to find a tensor, actually not a single floating point number, right? So this is actually the beauty of AutoGrad. You cannot go out of the tensor operations at any step. You have to do everything inside the tensor to keep track of forward computational graph, and then propagate backwards, right? So yeah, I've calculated the rows and columns and dimensions and output shape. So output shape is something that I'll be returning from this method, right? And output shape is obviously going to be like this. Is yeah, the important part is, let me show you a very important thing over here. So you know what, initially array was looking like something something like this: 1 2 3, maybe 4 5 and 6 7 8 9, maybe something like this. This was our initial matrix, and when we applied tensor mean on it, the output shape would be what? Number of rows times a single column, because this entire thing will be reduced, to only one number. Because what we're doing, actually we're taking the sum and dividing it. For example, if I take it here, so 1 plus 3 3, 3 plus 3 6, 6 divided by 3, and this index, at this index the value is going to be 2, right? So I'm getting all the number of rows but only one number of columns. So that's why I defined the output shape over here as 1. I hope this makes sense, right? And then I went ahead and allocated some space for it, and then I created a tensor out of it using tensor create new, which will initialize the parents, the operations, and everything with null values, and then we build our graph. So in case if this A requires gradient, then definitely this output would also require gradient equals true. So if I've put a check over here, so now I'm going to build a computational graph over here, define requires gradient. The first thing that I'm going to do obviously is the output will also require the gradient, and that is true for now. And then I've defined the number of parents. Obviously only one tensor is dependent, so yeah, only one parent, and let's define some space for them as well. So tensor pointer, because our initial array consisting of addresses of the tensor structures, right? So that's why I'm defining I'm allocating a tensor pointer space instead of just raw tensor, right? I hope that makes sense too. So at 0 index obviously is going to be A, only one parent, and then I've defined the operations. I took the space from arena and then defined operation backward is tensor mean backward. So this will be pointing towards mean backward, right? Which I'll write in the backward pass. And then we have operations defined over here. I've just added this to our tensor class parameter, and then I went ahead and ops grad is equals to arena, defined some gradient space as well, since we know that this is actually the shape, and then likewise we've defined the actual gradient. Right now I need to fill these. Well, we can now you can guess that what I'll be doing inside tensor mean backward. It will be just populating this tensor, right? This calculating the gradients, right? Yeah. And this actually is the logic for actual computation of the mean. What I do actually, as like I mentioned earlier, that I grab the row pointer, which is a flash starting address plus row times columns, and then I took a float sum, initializing from 0 and then row mean. I should not do this, by the way. I can directly just populate it over here divided by number of columns, but I took an extra variable just for readability and something simple, and I just populated this R, nothing else. So it's taking row wise mean, just like I mentioned earlier. So this was the mun method, and let me show you another method. So tensor add. So this is our new method. So tensor add also got changed. So you can see that, I started implementing only one token ID, and then processing it to embedding dimensions, and then extracting some contextual and semantic meaning off of it using some multi-head attentions, right? So the code keeps on expanding and expanding and expanding on daily basis. That's why you see Pytorch humongous code, because they keep on embedding. So it's a full-fledged framework. They optimize things, they put checks, they put validations, assertions, they have ton of different configuration, constant um, files and everything. But right now we are at that stage that we work only on core logic. Once it's completed, then we'll refactor this code. We'll create another branch which will be refactoring everything, right? So I hope these things make sense to you, right? In case if they don't, you can ask me in the comment section and let's build this together. You can always put up great session, like some of our subscribers, they're giving an awesome suggestions which are really helpful, and I have just I just keep on exploring the code. Okay, yeah, this thing I can do better. Okay, so we just work as a community, and I invite you guys as well to collaborate in this great project, which is implemented in C. And mind you, nobody has ever implemented transformers framework in C. PyTorch uses A10, which is written in C++, not in C, and some part, which is actually a core part of engine level C++. Rest 70-80% of C++ is PyTorch, which is in Python, right? Karpathy wrote this in C, but that was actually a minimal, you can say, runtime, a highly optimized C code which just runs transformer model. It's not a framework. It doesn't have a modular architecture or something, and nobody else have done this. So this is the first time we're implementing this in C. In case you find a repo that implements transformers in C, just to let me know. Okay, there was actually a side information. All right, so tensor add receives the arena obviously because it's got to take some memory for output matrix. Tensor A, tensor B. First of all, we assert whether the shape of first metric equals. So I was making a mistake over here. Let me show you a very cool thing. So what I was doing actually, I was doing something like this: assert A shape equals B shape. I was doing something like this, but later when I was actually reading this code, I got to know that A and B both are pointers, so we cannot, you know, uh, we cannot actually compare the shape of the pointers. Instead, we just went ahead and used the indexes for 0th and 0 bytes and first byte, right? First bytes. All right, so I hope I'm able to convey the idea. So we have dimensions, we have rows and columns, we have output shape. We have output shape something like this, which is populated from rows and column. Obviously, if you're just element wise adding two tensors, the shape is going to be same as A or B, whatever you want to take. So define the shape. Requires grad any of them or condition requires grad equals to output will require grad, that's for sure. Two parents, okay, makes sense. Define operations, just populate the ops and point towards the backward method, which will write in backward pass, and create the gradients and just add the logic over here. Same for tensor subtract, just one difference, just one index, one character different, and this subtract over here, right? And this was actually working fine. And now we have written three methods: subtract, mean, um, addition, and there's only one left, that is standard deviation, which is actually I just shown you the formula over here. I don't exactly remember for x hat, but something like x minus mean divided by I think square root of variance, something like this, but this gets cancelled. I guess it's x minus mean over standard deviation. This whole thing called standard deviation, by the way. This square is only variance or something. We'll check this later. Plus epsilon. right? This is our x hat, and then alpha times x hat plus beta. This is our y, and dy is going to be our derivative of this, which we'll be working on later. So this was actually the idea right now. I'm still working on this. Fingers crossed to me. Wish me luck to complete this, because once we are able to do this we just can certainly stamp this as a framework written purely in C. And who knows that if I create the Python bindings as well in future, and maybe one day we'll be using this for a framework with benchmarks, source, and everything, and optimizations and everything. So I need your support, guys. Thank you so much for watching and commenting and liking my stuff, and we'll see you in the next video. Take care. Bye.